What is the Doppler effect? And how does frequency change due to the Doppler effect? When the source of sound and the observer of the sound are both stationary, meaning not moving, the observer perceives or hears the actual frequency emitted by the source. Whatever the source is putting out, in this case 750 hertz, that's what the observer hears. But if either the observer or the source or both are moving, the frequency perceived is not that which is omitted. So in this example, you have the source of sound putting out 750 hertz, but they're moving towards the observer. And by moving, that changes the frequency observed by the observer. So the motion causes the perceived frequency to change, and this change is called the Doppler effect. And the change in frequency, we refer to that as a Doppler shift. So here's an illustration of a fire truck blaring its siren. Now when it's stationary, the sound waves being emitted in all directions, three-dimensionally, and somebody behind the fire truck hears whatever the person standing in front of the fire truck hears. There is no difference. But if the fire truck would be moving towards the right of the picture, what happens is as the sound is emitted towards the back of the truck or away from the direction of the movement, what happens is these waves now have to travel an additional distance because the sound is moving away. And in front of the truck, because the truck is moving forward, what happens is are the waves become pushed closer together. So as the waves are emitted, the truck is catching up to those waves. Consequently, what happens is the wavelength in front of the truck becomes smaller, and if we lower the wavelength, that's going to increase the pitch that we hear. And behind the truck, since you're moving away from those waves that are moving behind, what happens is that spreads the waves apart. And if you make the wavelength larger, the frequency decreases. So you probably noticed that if you're on the side of a road and someone blares a car horn as they pass you, or if you're watching NASCAR racing or something like that, and you hear the sound, the vibration of the engine, you're going to hear as the car or the siren comes towards you, you will hear a high pitch as it moves away from you, you'll hear a lower pitch. It'll be something like, and that's probably a sound that you're familiar with. As the vehicle approaches you, there's a high pitch, and when the vehicle moves away from you, there's that low pitch. So as the truck moves forward, what happens is moving away from the sound waves causes the wavelength to lengthen, and moving with the sound wave causes the wavelength to become compressed or shortened. Consequently, moving with the waves causes a high frequency, and moving away from the sound that's being emitted causes the frequency to be perceived by the observer as being lower in frequency. Now, let's have a look at how to calculate these things. So what is the frequency observed or perceived when the source moves towards the observer? So you have the observer here, and the source is moving towards the observer, like in the previous diagram. So here's a proof showing how we obtain the final formula. So the observed wavelength, because the wavelength is compressed, the observed wavelength, O for observed, is equal to whatever the original wavelength was of the sound, minus the distance that the source is moving times time. So this is, of course, from the formula velocity is equal to distance divided by time. So this is the distance that we take away from the original wavelength. So the amount, lambda, is reduced by that amount because the source is moving. So if we take this equation, what we can do is we can substitute the time of travel, time that that wave is traveling, using the velocity equation. Velocity is distance divided by time, and the velocity is going to be the speed of sound. Now, because of the V's and all the letters we have here, I'm making this V fancy just so to distinguish it from the other velocities. So we'll just put bars over the across the V. So if we continue this proof here, we can take the speed of sound is equal to the product of wavelength and frequency. In this case, it would be the wavelength and frequency of the observed sound, or we can rearrange this in terms of frequency. So the observed frequency is the speed of sound divided by the observed wavelength. Now the observed wavelength, we said, is equal to the original wavelength minus the reduction in the size of that wave. So we can substitute that lambda O in the equation. So we just take that and move it down to the bottom to the, I guess that would be the denominator. And we have a t for the period, and we can substitute that with frequency, because period is equal to 1 over frequency. So we have a substitution. So our equation for what is the observed frequency is now forming. And what we're going to do is we're going to get rid of the wavelength because it's just too many variables in our equation. We want our final equation to be as simple as possible. So wavelength is equal to speed of sound divided by frequency. And again, that's the velocity equation in terms of wavelength and frequency. And moving over here, we do that substitution. So that's the substituted part. And because we have frequency of the source, the original source, original sound, we can factor that out, 1 over f. And once we factor it out, we can flip it over to the top. And then what we could do is we can divide the top and bottom by the speed of sound. So v divided by v is 1, v divided by v is 1 again, and vs divided by v is vs divided by v. So this is typically the final form of the equation, where the observed frequency is equal to the source, the frequency of the source, the original frequency, multiplied by the contents of those parentheses. So what's important here, we need to know how fast the source is moving towards the observer and divide that by the speed of sound. So this formula applies to the source moving towards the observer. Now you may be concerned, yes, I'm going to give those formulas to you on a test. Now what happens if the source is moving away from the observer? I'm not going to go through the derivation of the formula. I'm just going to give you the rest of the formulas. All of these are derived in your textbook if that interests you. I'm not going to require the derivation of any particular one, but I do want you to understand how to do that in general terms. So the difference between the two formulas, if you look back in your notes, instead of having a negative here, we now have a positive. So we're adding, so that would be moving away. You need to figure out how to remember these formulas, how to interpret the formulas. Okay, I'll give you the formulas, but you are going to have to pick the right formula for the right scenario. So one way you can remember this is if you're moving away from the observer, the frequency should drop, right? It should be a lower pitch as you're moving away from the observer. So remember that. So think of the concept and use your understanding of the concept to understand how to use the formulas. So we're going to have a plus there. And what's the mathematical consequence of having the plus there? The denominator gets larger, So the frequency, the observed frequency, is going to be less than the frequency of the source. The pitch will be lower. Now, what if the observer is moving towards a stationary source? Well, we know that if the observer is moving towards a stationary source, we're bunching up the waves, so the wavelength is smaller, so the frequency should be higher. So the observed frequency is greater than the frequency of the source. And this is the formula, and the difference here is we're working with the speed of the observer instead of the speed of the source. And here is moving away from the source. And finally, what happens if both the source and the observer are moving at the same time? And you get this formula here that you're going to have to deal with. And again, I'll give you the formulas. You just have to know how to interpret them and how to use them to solve your problems. So this is written in a generic form where you have one plus or minus and the rest of it. Now, how do we interpret? When do we use plus? When do you use minus? Well, the top refers to the effect of the observer, and the bottom refers to the effect of the speed of the source. So you're going to use positive when the observer moves towards, and you're going to use negative when the observer moves away. Okay, now if both are moving, both of them can be moving towards, or one could be chasing after the other in that direction, or this could be chasing in that direction. Okay, so that's why we have the pluses and minus, and there's different combinations you can have depending on that scenario. Towards, both away, chasing this way or chasing that way. Okay, so here are the 4 ways of interpreting the signage in the formula.